Welcome to AI-driven forward error correction for multi-cloud networking. So my name is Fatih Nar. I'm a senior architect or chief architect, however you like to call me, at Red Hat. This is my 3.7 years at Red Hat. Before I was part of Google Cloud, before it was Verizon, before many lives ago it was Ubuntu and Ericsson and so on and so forth. So last, I would say, decade, I have been heavily focusing on the operation support side of the house for networking with the switching fabric, the applications, the OS, all that observability. And my previous session here was around observability for edge. If you missed it, you can go watch the replay if you want. Feel free to reach out to me over LinkedIn and connect and for the questions. So I have a partner in crime here, do the majority of the presentation, but let me give you a quick, interesting story how me as part of Red Hat being engaged with the MIT/Steinwurf. So I was at a conference. The reason I'm telling you, there's a reason I'm telling you this story, which I'm going to explain later. So I was at a conference and I was presenting in an undisclosed location. And after my presentation, a lady showed up, very serious, she said, we need to talk. And I looked at her badge. It was saying IRS. I said, shit. So if you're not familiar with the lifestyle in the US, being chased by IRS is one step above being a most wanted in the FBI, i.e. you can be a serial killer, but being chased directly in person in a conference by IRS is something phenomenal. Anyway, so after my presentation, I was texting my wife, did we scrub our tax returns this year or something in the last 5 years? And then she said, no. Anyway, so I came up with her and she explained that, hey, the problems you were talking about, the packet drops between the network boundaries and also the long distance performance of the network packet transmission for latency, I might have a good friend for you to talk to. And then she introduced me to Professor Muriel Medard at MIT. And this is how this collaboration started. The reason I'm telling you this, I have a green sticker here. If you want to collaborate, work with us, or come up with a solution for your needs, feel free to come up and talk. We are really open-minded people, open-minded company. So I will let my partner to introduce himself quick.
Hello. I'm Peter. I'm a software engineer at Steinwurf, the head of our application development. And I love to work with, there's some spelling mistakes there, but I'm a software engineer that loves software and network applications, and especially real-time applications where we optimize for, let's say, online gaming or video conferences, remote driving cars, and so on. So, yeah, this is just quickly me, yeah.
So the importance of network fabric performance is mainly, at this context, is mainly around, am I able to deliver my packets in proper order, in timely fashion? If I can I recover those packets at the receiving end? So if I can, without retransmitting it, it will save me a lot of time, i.e. it's going to lower my latency, i.e. it's going to save me from wasting my bandwidth. So that is the thing. If you have a proper mechanism to reconstruct the packets or efficiently transmit the packets to a long distance destination, or it could be over it could be a short distance but over multiple hops. So if you think about the edge perspective from cloud, say from AWS or Google Cloud, you're going over direct peering, and then multiple hops to the edge is not that necessarily dark fiber. There are a lot of hops with different transmission technologies where you're going to experience a lot of packet drops or latency issues. So as being de facto platform for applications to be hosted, Kubernetes has a construct called CNI, Container Native Interface, if you're familiar with that. And we have a construct called multiple interfaces. So while we were collaborating with the MIT/Steinwurf, so we wanted to do something really fast forward and to see the benefit of their algorithm. So what we did as Red Hat, we create the additional CNI, add-on CNI on the secondary interface, Net 1 interface. If you're familiar with the Kubernetes, the primary interface is the primary CNI. We are usually using OVN Kubernetes for ETH0. The additional interfaces for multi start with Net 1, Net 2, and goes on and so forth. Usually when you see a network-intensive application using additional interfaces, it could be MAC VLAN, IP VLAN, SRAOV, and so on and so forth. Even those additional interfaces say the best approach, best network performance is SRAOV. You're still subject to packet drops over multiple hops or latencies. So at this point, we carve down and create a brand new CNI with the Steinwurf overlay on the additional network interface, where they introduced their FEC as an add-on component into a container interface. So this is a good thing, because if you have already clusters up there with the applications, you can add on this component as an additional interface, start using it rather than asking your system admin to redeploy your cluster with a brand new CNI, which is a lot of effort needed, a lot of verification needed. All right, this is where I hand over.
Yeah. Okay. Yeah, hello again. My name is Peter, and I'm here today to present the results of the experiments we made in collaboration with Red Hat. So who am I? I'm a Danish software engineer at a company named Steinwurf, where I'm the head of our application development. Steinwurf is a company based in Denmark and specializes in network optimization, especially for use cases where low latency matters. Our primary focus for the last 10 to 15 years has been in the realm of FEC algorithms. In that time, we have developed an algorithm that beats all other alternative FEC available on the market right now, both in regards to bandwidth utilization, but especially in regards to latency. So let's first take a look at the results. The first picture at the top right shows a test using, we're doing an IPEF test with UDP.
If I chime in. So the test bed is mainly twofold. One is the streaming servers deployed in Google Cloud in India, and consumer is in US. So we are streaming from India literally to a US client. So normally you will see packet drops or latency because of intercontinental communication. This is what you're looking at right now.
Yeah. So yeah. The two machines are used for the experiment were located in two different data centers, one in, as Fatih said, in US and then the other one in India. With some traffic control, net emulation, we added an artificial packet loss of 10% between the two machines. We tested with a target throughput of 15 megabits, so with 10% packet loss and no FEC, we got an actually throughput of 40 megabits and a measurable packet loss of 10%. We then added our FEC and got the UDP back to 15 megabit, 0% packet loss, and without adding any noticeable latency. So this is already awesome, right? But if we then take at the TCP test, which is the one below, I know this is maybe a bit blurry, but we do the same testing setup where we as adding 10% packet loss and a target throughput of 15 megabit, but we only get an actually throughput of 384 kilobit. Why is that? Well, I will dive into that more deep in a second, but just quickly explain, it's because TCP is a fully reliable transport protocol, whereas UDP is not. UDP will just ignore any packet loss in transmission, leaving it to the application to figure out a strategy for dealing with it. TCP is built around retransmission, meaning that if any packet is lost, TCP will ensure it gets retransmitted. This is, of course, comes with the cost of added latency and extra bandwidth if the packet loss, of course. But it also results in this huge drop in throughput. And this, let me just choose a second. But if we add back in the FEC between the two TCP peers, we get the throughput back to 48 megabit, which is almost the full 15 megabit throughput target we had. And it's also worth mentioning, even though it's not that clear from these results, that the whole transmission is much more stable. And this is because by using FEC, we remove the packet losses, and so the connection seems more stable. the packet losses are fixed before entering the receiver, the TCP receiver, state machine. So to TCP, it just seems that there's no packet loss on the connections, and so it doesn't start to misbehave. It's also, we also have a speed test below the TCP test that shows that a significant improvement in the jitter, which is also a killer for real-time applications. So let's quickly have a rundown of how TCP works, and I know this is a somewhat simplified explanation of the TCP protocol, but I don't want to spend too much time on this, so let's get started. Whenever the sender on this, the sender on the left side sends a packet to the receiver on the right, and an acknowledgement is sent back to the sender. This confirms to the sender that the packet has arrived successfully and can now forget about that packet. If a packet is sent but never arrives on the receiver side, a timer on the sender will be started, and after it expires, a repeat of the packet is sent. A rule of thumb is that the timer duration is between 3 and 4 RTT, and RTT being the round-trip time between the sender and receiver. Let's say, for example, we have a link latency of 100 milliseconds. This will give us an RTT of 200 milliseconds, and in the case of 400 RTT, 800 milliseconds. It's also possible to detect the packet loss before the timer by packets arriving on the receiver side that will reveal the data gap in the stream. This will make the receiver send a repeat request to the sender, costing at least 1 RTT. So with a link latency of 100 milliseconds, that will be a wait time of at least 200 milliseconds. This adds a latency to the packet, sure, but it's also the real killer for the throughput, because the TCP receiver kind of just has to stop and wait for the packets to successfully deliver any further packets to the application. And what if the retransmission is also lost? So then it starts to add up, and the fact that it has to wait, the throughput goes down, and yeah, it really strengthens the throughput and turns down the throughput, yeah. TCP also has congestion control, which is essentially tries to find the throughput limit available in the network as not to overflood it. But in my opinion, at least, it has a crucial fault in its design of treating any packet loss as a sign of hitting this limit, causing TCP to also proactively squeeze the pipe and decrease the throughput even further. There are newer congestion controls algorithms which that tries to solve this problem by not being as sensitive to packet loss, but currently none of these are in widespread use. An example of such an algorithm could be BBR, that looks at the RTT instead of packet loss. But none of these optimized algorithms are used as the default congestion controls in any major operation systems. So most often applications are running on old school congestion controls. So the solution is simple: remove the packet loss, and you don't need retransmissions. If you don't need retransmissions, you will get a more stable connection, allowing the data to flow undisturbed. And this is what we do with FEC by setting it in between the sender and receiver, proactively fixing the packet losses. Now, you may be sitting there thinking, Peter, this is all good and well, but I don't know what FEC is. So let's take a look at what FEC stands for. FEC stands for Forward Erasure Correction and has roots in the coding theory field. There's also something called Forward Error Correction in the coding theory field, but it's not the same as Forward Erasure Correction. In Forward Erasure Correction, we focus on fixing lost data, whereas in Forward Error Correction, we focus on fixing errors in the data. People often get these two confused because they are closely related, and they also share the same acronym, which doesn't help. I also sometimes slips up and say error correction instead of erasure correction. But just know that when I'm saying FEC, I'm talking about forward erasure correction. So FEC is essentially just algebra. that, let's say you have two packets, A and B. You add those two together to form a new packet, C. A and B as application data. We call them systematic packets. And C is a sum of A and B, and we call that repair packets. If we send all three packets, but one of them get lost, we can still recover and reconstruct all three packets by solving the equation. We can also construct equations by any number of systematic symbols. But as we add more, we also increase the chance of being able to solve the equations, which would happen if we were to lose more than one packet from the equation. This we consider a weaker code, whereas a code with less systematic packets is considered a stronger one. But we can also do better by bringing in some more sophisticated math, such as system of linear equations and overlapping equations, where the systematic packets are part of multiple system or repair packets. My dear colleague Muriel, that Fatih talked about, and her team at MIT invented what is called RLNC, random linear network coding. Old school coding techniques utilizes fixed-sized blocks for coding repair packets, which has the drawback of having to need enough packets to construct the actual repair packets. This may cause latency and so on. RLNC eliminates this need and is a simpler and, in my opinion, also a much more sophisticated way to do FEC coding compared to other block-based alternatives, such as Reed-Solomon. But don't worry, I won't bore you by going into more details. Also, I won't consider myself smart enough to even try to explain this. But if you're interested in learning more about RLNC, there's a lot of good videos on YouTube with Muriel actually explaining RLNC herself. So instead of digging too deep, let's now ask the question, what if I'm using FEC, but there's currently no packet loss? Sure, this is the main drawback of FEC. By sending the repair packets, you get a bandwidth overhead, but only in the case you don't need it. If the packets actually lost, then the repair packets are useful. So then they are not overhead. They're not considered waste. But this is just a side effect caused by the very nature of how FEC works. You simply need to send more data. But we also have a solution for this that I will get back to later. Just know that FEC is not magic. You need some computing power for the coding, and most noticeable, some additional bandwidth. So now let's talk about the good sides of FEC and why it's so awesome. Sure, better throughput in the case of TCP, but that is what that mainly correlates to is the improved latency. You don't need to retransmit the data, you just need to add enough upfront repair to handle the network loss. This is especially crucial for better user experience for real-time applications such as online gaming, video conferences, and remote driving. I guess we all appreciate that a remote-driven car reacts as quickly as possible to a vehicle hitting its brakes in front of it. This brings me to the topic of real-time reliability, which is what we care the most about at Steinwurf. Instead of just measuring how many packets are lost in transmission or how many was received in transmission, we instead focus on how many packets was received in time or how much data was received in time. So to determine if a packet arrives in time, we need a time budget. Time budget is the time span a packet has available to successfully arrive at the receiver. If any packet is received after the given time period, the packet is essentially considered lost. Okay, so for real-time application, we want a low time budget. The average human's reaction time is 250 milliseconds. To give you some perspective of how long that is, the average time spent for blinking is between 100 and 400 milliseconds. So I guess we can say we want the data to be transmitted in the blink of an eye. but the time budget, of course, depends on the application, and there's no universal fixed definition of what this budget must be, at least not that I know of. So to calculate the real-time application, we take the total number of packets received in time and divide that by the total number of packets sent. This will give us the real-time reliability. Just an example. So let's say we sent 200 packets, but only 190 was received in time. That leaves us with a real-time reliability of 95%. This is the main KPI we use to measure the performance when developing and testing our algorithms. Now, I want to get back to the overhead problem caused by FEC. By adding upfront repair, we cause an overhead, but we only just need to add just enough, if any. What I'm getting at is that we can adaptively adjust the amount of FEC and make it fit to what the packet loss is on the current link that the data is transmitted on. And for this, we use AI, such as statistics, to calculate the amount needed, and also reinforcement learning to predict losses so that we can adjust the FEC in time. Even though we show that removing the need for retransmission in a TCP session greatly improved its throughput, we don't consider retransmissions a bad thing at Steinwurf. Retransmissions are bad in the case of TCP because TCP is a fully reliable protocol. The data stream just stops at the receiver until any lost data is recovered. But for many real-time applications, we don't care about the data if it gets too old. We want to instead just drop the data and continue. So let's not discard retransmission as a viable solution. Retransmission are really good in the case of burst of packet losses, where multiple packet losses occur right after each other. In this case, retransmission are just excellent. Also, in terms of bandwidth, retransmission can be beneficial if the loss percentage is low enough. You can also mix FEC with the retransmission and make coded retransmission, getting a more efficient retransmission algorithm. There's also the possibility to use multiple links. Consider a remotely driven car driving around in the city with multiple wireless modems. We don't want to send the data out on all of them, at least not all the data. That might be too costly in terms of bandwidth consumption. Instead, let's choose the best one. And if the signal between that modem and its tower is broken by, let's say, driving in front of a building, the other modem still have a great connectivity. So let's utilize this by switching over to the next best alternative link. Even though the loss of a connection seems to happen instantly to us humans, it is most often possible for the computers to detect and switch in time, making it mostly unnoticeable. We can also use multiple links to smartly distribute repair packets, utilizing the fact that the packet losses on the different links are not correlated, and therefore not happens at the same time on every link. If we then bring these three mechanisms together, FEC, retransmissions, and multilink, and also mix in some link monitoring with the AI to adaptively react to the changing conditions on the links, you can create a next generation transport protocol. And this is, of course, what we did at Steinwurf with our transport protocol called RAFT. I will also just add that RAFT is running on UDP. So it does need to run on UDP, but for network applications, we always use UDP. We just need to run on a network that is not having any other types of reliability mechanisms. But we can still sit in between, let's say TCP, we can sit in between there and help. This one. What we also have made is our solution called RAMP. RAMP is a component-based pipeline builder that makes it possible to quickly create network tunnels to test and evaluate different algorithms and protocols, such as our own protocol Raft. You can simply drag and drop components and string them together to form a tunnel. You can add I/O components such as UDP and TCP and TONDEP interfaces to get the data in and out of the pipelines. You can then add impairment components to add artificial packet loss, latency, and bandwidth limits. You can also add monitoring components to track latency, packet loss, and throughput. By putting together different components together in our beautiful, intuitive GUI, it is possible to quickly get insights into how different algorithms and protocols behave in various scenarios. And ultimately, it also gives you the ability to integrate them into your own real-time application and utilize, get the advantages of our real-time protocols and algorithms, such as we also have, now I'm talking about our protocol, but we also have standalone components to just adding hard-fixed, hard-configured FEC algorithms. It's called Rely, but it's not in these slides, though. The RAM CNI is the integration of our RAM solution into the Kubernetes and OpenShift environment that we created in collaboration with Red Hat. It is what we used for the test that we did. We saw the results of earlier. We did only use the FEC part of Raft for that, though. Adding an extra layer of retransmission onto TCP did cause some strange behavior, so we just stick with the FEC. And also regarding multilink, I don't know why we didn't try that, but we did, and I think we just were very satisfied with the results of the FEC. But in this scenario, with the machine located in the US and another one in India, it may have made sense to test with one link over the Atlantic and another one over the Pacific. I also just quickly want to show the results again, and hopefully now the results won't seem so strange anymore. If we remove the packet loss from TCP, the throughput goes up, even though we are adding some overhead. The overhead is fundamentally required for data to be reliably transmitted. Without the FEC, we will just have the overhead of the TCP retransmissions instead. So to conclude, by using AI to adaptively adjust the FEC, we achieved a significant improvement in terms of stability and reliability. Raft is the protocol that makes it possible for us to do this. RAMP CNI is the practical solution for applying it to the Kubernetes and OpenShift environments. We hope that this work together with Red Hat will be the base for us, which we can build upon to further leverage AI and improve resiliency in even more. And that's it. Thank you so much for listening, and I hope it has been interesting. Thank you.
One add-on to this is, although our testbed was based on OpenShift Kubernetes, this technology, this approach could easily be applied to a single OS. Say you have a RHEL for Edge in Linux at Edge sitting, there's no Kubernetes. You can embed this capability as a package installation and start leveraging it. So this is applicable not only Kubernetes CNIs, but also standalone nodes with Linux on it. All right.
Yes, that's correct. I don't know, yeah.
So one question, so nice talk, thank you. Have you looked at the overall fairness aspect of what you're doing? Because the main benefit of what you obviously receive if you're doing forward error correction or forward or FEC on your connection, then you survive the packet drop and everybody else will back off, right? So the benefit that you get is everybody else's downside that is on the same link. So have you run your protocol, FEC plus TCP, in a scenario where you indeed do where you're competing with yourself and not with somebody that is obviously weaker because TCP won't survive the packet loss, so everybody else backs off. So I think you get the benefit because a lot of people get the downside. So I'm just wondering whether you looked at the fairness aspects.
So just to make sure that I understand what you're getting at is we only have so much bandwidth to use, right? So if we start to use more bandwidth, we start to remove the priority from others.
So if you have 10 connections, and all the 10 connections, assuming that the RTT is the same, all these 10 connections will back off at the same time. If one of these 10 connections is FEC enabled, that connection will not back off. 9 connections will back off, and that means your 10th connection obviously gets far more bandwidth because it's not backing off, it's backing off later on. So that means from a throughput perspective, you obviously get that benefit. But I'm just wondering if you are running against yourself instead of a quote-unquote weaker competitor like with pure TCP, whether these benefits are still holding, because then everybody will back off at the same time again, plus you have the overhead.
It's a really good question and a really good observation.
But you got to consider the multipath, right?
Also that.
So if you have multipath, you don't need to worry. Yeah, exactly. But fairness over the multipath rather than a single path, right?
But also to add to it, we of course know that if you are running on a link that has reached its max capacity, it doesn't make sense to add FEC in, because then it actually starts to get worse. So it does require that you have bandwidth, enough extra bandwidth available on the link. But we also have, for the protocol, we also have limits we can set. We can also set how much we want to use, so it doesn't just go haywire and take everything. So, yeah. Any other questions? Yeah.
Hey, I just had a question about the AI part. Could you explain a little bit more about how the AI informs maybe that code rate, or versus just using maybe a lookup table, or because I assume your features are right latency, jitter, packet drops, retransmissions. So why and how AI?
So I'm not the brain of the AI part, so I'm not really in a position to actually explain it. But I like to think of what we're trying to do with the AI part to predict the packet losses is kind of the same as in quantitative financial world, where you're predicting if a packet is lost or a packet is received and when it happens. But and why it's remind of me of trading is because either the price goes up or down. But yeah.
Okay. Is the output of the AI model or some model to define that code rate, or kind of how does that input into your FEC?
Again, this is, I only have a very weak understanding of this. This is my colleagues that are doing this, but it's kind of, I don't want it to, because maybe I'm getting it wrong. Yeah.
No problem. So I just have another quick question.
Yeah,
is there, so with the Raft protocol, you said it was UDP based, is that right?
Yeah, Raft is running on UDP mostly, but it can run on any, actually. It doesn't care about the underlying network.
Is there a, does any peering need to occur with, say, the receiver side?
So the Raft protocol has a handshake in it that it uses. So, yeah. If the connection is lost, then the two machines, state machines, the two Raft state machines need to reset. But, yeah.
Gotcha. Thank you.
Yeah. Any other questions? Okay. Super.
All good?
Yeah.
All right.
Yeah. Thank you.
Thank you.